welcome to The Explainer. Today we're diving into a really fundamental question in AI safety. How do you possibly build a defense against an attack you can't even see? We're going to break down a paper that offers a solution that's as simple as it is powerful. So let's start with something that might sound a little weird. These incredible, state-of-the-art AI models, the ones that can beat humans at all sorts of tasks, are also, believe it or not, super fragile. They're surprisingly easy to fool. The authors of this paper put it perfectly. An attacker can make these tiny, microscopic changes to an image, changes that you and I would never notice, and completely trick a neural network. We're talking about taking a picture of a panda, changing a few pixels, and suddenly the AI is 100% convinced it's looking at a given. It's wild. And this crazy vulnerability has kicked off what everyone in the field calls the adversarial arms race. It's this constant cat-and-mouse game between AI defenders and AI attackers. You've seen this cycle before, right? A new defense gets proposed, and everyone gets excited. But then, sure enough, a few months later, someone finds a new way to break it. It's this frustrating loop that led researchers to chase a different kind of goal: to stop building defenses that just seem to work and start building defenses that come with a formal mathematical guarantee. A certified defense. Which brings us right back to the core problem. I mean, if these attacks are literally invisible, how can you build a defense that's actually going to last, instead of just being another temporary patch? Well, the solution this paper comes up with is it's so elegant and completely counterintuitive. The idea is, instead of trying to find and block the tiny attack, you just drown it out completely. And this slide, like here, shows you exactly what I mean. On the left, a nice, clean image. On the right, that same image, but we've just blasted it with a ton of random staticky noise. The big idea here is that all of that random noise can just swallow up the tiny, carefully crafted noise from the attacker. By adding all this random Gaussian noise, the attacker's clever little change just becomes statistically meaningless. It gets completely lost in the static. So what this technique actually does is create a whole new classifier. The paper calls it G, the smoothed classifier. And it's built using the original fragile one, which we'll call F. A good way to think about it is that F is like a single brilliant but vulnerable expert, while G is like a new, super robust committee that uses that expert's advice in a much smarter way. So how does this committee work? It's actually dead simple. To classify an image, you just show the original classifier F thousands of different noisy versions of that image. And then you just hold an election. The class that gets the most votes becomes the final, robust prediction of our new smoothed classifier G. But here's the really cool part. This isn't just some clever trick or a neat idea. What makes it so powerful is that it comes with a real mathematical guarantee, a provable shield of protection around every single prediction it makes. Okay, now don't let the formula scare you off. This is what gives us that certified radius. It tells us exactly how big of an attack our new classifier can handle. We're not going to walk through the proof, but let's break down what these variables mean, because that's where all the intuition is. First up, you've got sigma. That's simply how much random noise we're adding. You can think of it like a dial you can turn up or down. Cranking up the noise can give you more protection. Next up is PA. This just represents the confidence in the winning vote. So if like 99% of the noisy images were all classified as panda, our PA would be super high. It means the committee has a very clear winner. And finally, you have PB, which is the probability for the runner-up class. The real magic here is the gap between PA and PB. If the winner gets 99% of the votes and the second-place contender gets less than 1%, well, that's a landslide. That huge margin of victory means an attacker needs to make a much, much bigger change to flip the vote, which gives us a bigger certified radius. And this image makes it all just click. For a super simple classifier, one that just draws a straight line to separate two classes, the certified radius from that big formula turns out to be the exact geometric distance from our input to that dividing line. The math lines up perfectly with what we can see. So the theory is really elegant. But how do we actually turn this into an algorithm that works in the real world? Okay, so here's the catch. For a massive neural network with millions or billions of parameters, you can't actually calculate those exact probabilities, PA and PB. The computation is just impossible. So we've got to find a reliable way to estimate them. And that's exactly what the certify algorithm does. It uses a statistical trick called Monte Carlo sampling. First, it takes a small batch of noisy samples just to get a good guess at what the winning class is. Then, it takes a huge number of new samples, like 100,000, to get a really high confidence estimate for that winner's probability. And with that estimate, it can calculate a radius that it knows is correct with, say, 99.9% probability. Now, this is where randomized smoothing really just pulls away from all the other methods. A lot of other certified defenses really struggle when you try to apply them to big, messy problems. This one, though, it thrives. And just look at these results. This table shows the certified accuracy on ImageNet, which is this massive, notoriously difficult dataset. At the time this paper was published, no other certified defense had even come close to scaling to this level. To achieve a certified accuracy of 49% on ImageNet, that was a massive breakthrough for the whole field. The reason it scales so well comes back to its beautiful simplicity. The method is architecture agnostic, which is just a fancy way of saying it doesn't care what the base classifier looks like. It could be a simple model, or it could be a giant neural network with a billion parameters. You just wrap this technique around it, and it works. That's why it was the first to conquer ImageNet. This quote from the authors just nails the main takeaway. It brilliantly reframes the entire problem. It takes this really hard, unsolved problem of adversarial robustness and transforms it into a much more familiar problem, just getting a classifier to work well on noisy data. And that leaves us with a pretty provocative final thought, doesn't it? In this big race to build safe, reliable AI, maybe the answer isn't always another layer of complexity. Maybe the most powerful solutions are the ones, like randomized smoothing, that are built on a simple, provable, and principled foundation.